Welcome to the new semester for the picture language seminar. We're very happy to start online. You can see my office behind me. I wish I were there, but because of COVID, I can't be. And we have a number of interesting upcoming talks. We're going to continue next week with Nilanjana Datta and Avi Viggerson, Wenxing Ren, David Evans, and Chenghan Wang. And today it's a real pleasure to have Jinsong Wu. Jinsong visited 3 times at Harvard between 3 and 6 months. And he was at the University of New Hampshire before that, and also the Chinese Academy of Sciences. He's had been professor at the University of Science and Technology in FA, and now he's professor in the Harvard Institute for Advanced Study in Mathematics. Jinsong will talk today about his new paper, Inequalities in Fourier Analysis for Locally Compact Quantum Groups, which should soon be on the archive. He's one of the instigators and developers of the new subject of quantum Fourier analysis. And we're looking forward, Jinsong, very much to hear your talk. Jinsong.
Thanks for Professor Jeff's introduction. The title of my talk is Some Inequalities in Locally Compact Quantum Group. This is a part of quantum Fourier analysis. First, I'd like to briefly introduce the quantum Fourier analysis. Currently, we study several objects such as suffix fusion ring groups. We did not actually systematically study groups. Actually, we study locally compact quantum group here. They have some difference, and I'd like to use 3 columns to introduce them. One is the algebra itself. Suffix could be non-commutative on both sides, the dual sides itself. But usually we consider suffix plane algebra. Its dimension is finite. The measure on that is trace. Fusion ring. We consider here one side is commutative, the other side is non-commutative. And usually its dimension is finite. The measure on that is treasure. Actually, it's treasure state somehow. Groups could be commutative. I mean, the commutative means not the commutative group. I mean the functions. The algebra of all functions on group is commutative, and its dual is non-commutative. Usually, its dimension should be infinity. But since the algebra of functions is commutative, this measure usually is taken as trace. To generalize groups, there are several directions like test algebra, compact quantum group, and also suffix is a way to generalize groups, but finite group, not general group. Locally compact quantum group actually generalize them all. I mean, generalize all means generalize group, test algebra, compact quantum group, but not all suffixes, because suffix could be depth n or arbitrary depth. Locally compact quantum group compared with suffixes is usually is depth 2, but it's still hard enough because the algebra could be non-commutative on both sides, the itself and its dual, and the dimension usually is infinity. The more difficult part is that its measure usually is non-trivial. That means we need a lot of tools to handle its analysis. In this talk, we are going to talk about some inequalities. Most of them are already proved for suffixes. That means for finite case. Some of them is proved for a unimodular test algebra with trace. First, I'd like to introduce the definition of a locally compact quantum group. This definition is due to Customans and Bass in 2000 and 2003. A locally compact quantum group is a pair of the following three data: a polynomial algebra M and a co-multiplication data. A co-multiplication is somehow the multiplication on the dual. So here we have this process definition. It's a unit normal star homomorphism satisfies following co-associative law. And the third condition is the key. That means it has a left half weight phi and a right half weight percent on M. For compact group, due to our knowledge, for compact quantum group, due to our knowledge, it always has a half weight. But for general locally compact quantum group, we don't have this theory now. So we have to add this condition here. Now I'd like to introduce some special cases because actually this locally compact quantum group is a really big category. It generalizes locally compact group because when the polynomial M is abelian, then this is a locally compact group. I mean, this can be algebra of function on a group. If phi equal to percent, this locally compact group is called unimodular. If phi equal to percent is treasure, then we call it unimodular Katz algebra. This notation is due to a hope of Enoch and Schwartz. The Katz algebra is introduced by Katz van Niemann, Enoch, Schwartz independently. I will introduce the process definition of Katz algebra later. And a very interesting example is, or special case is compact quantum group. This is introduced actually by our knowledge in 1992. This is a very important example because most interesting examples in locally compact quantum group are known as compact quantum group. The other is the dual of compact quantum group, which is discrete quantum group. It's introduced by Van Der in 1996. I think, as I know, he introduced this in algebraic way, but there's no big difference for this discrete quantum group. Also, computable, I think is computable. Example is compact matrix quantum group. This is introduced by our knowledge. It has examples such as quantum SUQ, quantum permutation group. Quantum permutation group is used widely. It's introduced by Wang. Also, our knowledge actually did a lot of contribution for quantum groups. He also introduced non-compact quantum group such as quantum E2 group, quantum AX plus B group, and quantum AZ plus B group. They are very interesting and try to study its analysis. There are also some examples which are not quantum groups, such as matrix algebra, quantum torus. such like quantum torus. This is also an interesting quantum symmetry, but it's not in the category of locally compatible quantum. Recently, we developed a way to include this to this category, but not directly a compact locally compatible quantum group. Actually, it's a traced locally compatible quantum group. So maybe some technique for locally compatible can be applied for this quantum symmetry. Now I'd like to give you some notations and basic setup. We begin with the Gelfand-Naimark-Seeger construction. Here, because the left half weight is not a state, so we actually use same cycle construction. That means we have to use Tomita-Takis theory. This n phi gives us the finite value. N phi is this set with phi takes finite value on this x. By taking its this phi also gives us an inner product on this linear space. By taking its completion, we get a Hilbert space. This Hilbert space is very important because the formal algebra I'm acting on it is standard. With standard position, we have a lot of interesting results. We denote by this inclusion. We denote this inclusion map by lambda phi. Also, the modular automorphism for left half weight is sigma t phi. For the right half weight is sigma psi t. And there's a modular element between left half weight and right half weight. It's in this way. Psi equal to phi delta. Phi delta. Formally, psi equal to phi delta 1/2 dot delta 1/2. We denote G phi, the modular conjugation, lambda phi, the modular operates. This is a little different from the usual notation for Tomita-Takis theory because we use delta for the commutation. So this notation is very important in this locally compatible quantum group called multiplicative unitary. The multiplicative unitary is a unitary which is non-trivial. It's defined from the commutation. So the commutation can be written as a conjugate of this conjugate by this multiplicative unitary. By using this unitary, we can define the dual of this locally compatible quantum group. Its formal algebra is given by this algebra. And its commutation. Its commutation is given by a flip of the adjoint of this multiplicative unitary. Psi, the dual left half weight is from this x phi times L. X phi tensor L. L here is an identity, and the x phi is x dot phi acting on y x. So that means we can put this x to the right hand side actually. We identify the two vectors to get this dual left half weight. Then also we denote the j hat and the lambda hat to be modular conjugation and modular operates. The dual right half weight will be given later. We also have the unitary, the multiplicative unitary is in the tensor product of the formal algebra and is dual. If G is a group, then this W is simple. It's just it acting on a function to just multiply the group elements. Usually, we should have to get the multiplicative unitary to get a quantum group or a Hopf algebra. And our Fourier transform actually is defined from this multiplicative unitary. Next, I'd like to introduce the antipoint. The antipoint is defined from the commutation in this way. It also can be defined in this way. So this antipoint has polar decomposition. It is a multiplication of R times tau negative I over 2, where R is unitary antipoint, tau is the scaling automorphism. This is non-trivial because for Katz algebra or for group, there's no scaling automorphism. The endpoint is a unitary endpoint, but for general locally compact quantum group, there's a scaling automorphism. With unitary endpoint, we can take the right half weight to be phi composed with R. The phi is the left half weight. And also by using this unitary half weight, we can define the dual unitary half weight. Note that lambda omega equal to omega tensor L times W is dense in the dual. It's also called the Fourier representation. Also, the dual scaling automorphism is defined in this way. Then the dual endpoint is the multiplication of dual unitary endpoint and the dual scaling automorphism. And this time, the dual right half weight is taken to be the dual left half weight composed with the dual unitary endpoint. With this endpoint, we can define the Katz algebra in terms of locally compact quantum group. Then, if tau is trivial and delta, the modular element, is affiliated with the center, then we see this G is a Katz algebra. We also like to introduce some basic notation for some special automorphic group, because this automorphic group is very important. This rho T actually is composition of delta and scaling automorphism. it actually induces the dual modular automorphism by Kussmann and Bass. Tau t is actually is given by the dual modular automorphism, and the dual scaling automorphism actually is given by the modular automorphism directly. And per se, this is usual because it's implemented by this modular element, so it has this property. Also, this multiplicative unitary has this commuting relation. That means this actually is, if we put this side to the left-hand side, then it's this W is invariant and tau t, and the multiplication of tau t and the dual of tau t. There are also a lot of commuting relation between them. Our main technique to obtain this to obtain the inequalities is to use non-commutative LP space. There are three very important LP space. They are called interpolated LP space, and spatial LP space, and Hargroup LP space. Interpolated LP space is studied by Turp and Izumi and some others. But in Izumi's paper, he studied it in a completed way. So we also call it Izumi's LP space. Its advantage is that it can identify elements between LP space. But its disadvantage is that it cannot do multiplication. For the second and the third, the spatial LP space and Hargroup LP space, their advantage is that we can do multiplication. This is very important because if we have this trace, then if this is trace, if the weight is tracial, then we have no difference between them, and we can do a lot of analysis. But for the general case, we cannot simply identify that. For special case, for special LP space, it's first studied by Hom by introducing special derivatives. Then it introduced by Hilsum, his student, his student, in 1981. Compared with Hargroup's LP space, this LP space has this advantage. It does not change the underlying space, the underlying Hilbert space. I mean, for the Fourier algebra M. But for Hargroup's LP space, the underlying Hilbert space is changed to be a bigger one. But its advantage is that we can use the tracial case, then we can do some analysis by using the traces results. First, I'd like to briefly introduce interpolated LP space. There are infinitely many parameters to introduce this interpolated LP space. But here, we only interested in in the case that the parameter z equal to -1/2. We have this diagram because we have to consider the intersection between M and its radial. So we have to identify them. For an element x, roughly speaking, we put this x into M directly, okay? But we have to find the right way to put it into its radial. Then we put it in this way. X phi equal to phi dot x. That means we put this x on the right-hand side. We have to let this expression make sense. We have to add some lot of conditions, but I'm not going to express here. Put it to the right, we call it L phi. If we put it on the left, then we call it R phi. Then M, the radial of M and the M can be understood as an action on this R phi. So this diagram actually commutative. This is called compactable pair. This gives us a way to identify the intersection of, this gives us a way to understand the intersection of M and M's radial. This way is not unique. Actually, there are infinite many ways. Then with this way, can make some identification. We identify L1G to be the radial, L infinite G to be M, and the intersection of them is L phi. By using complex interpolation method, we can get LP. And the L2 actually is simply can be identified this H phi. L2 intersection with L infinity is N phi. And the L1 intersection with L2 is I phi, which are the normal linear functions. Also in the L2 satisfy this inequality. Because we can take the intersection, so there are many ways to identify elements. We use cosine t to use this inclusion, and use iota t to use to identify this to indicate this inclusion. So it does not tell us what's the difference between the LP space, right? Because we already identified that. Then this is the advantage for spatial LP space and Hargreaves LP space, because we can distinct them. If we let phi be a normal semi-finite faithful weight on the commutator M prime acting on H phi, very important notation is that is the spatial derivative. It tells us how the space changes. Then we can define this LP space. A very interesting dense subset is x d phi to the power 1 over p. For some proper x, there are a lot of conditions on this one. But roughly we can use this because in this 6, we will identify it with the elements in interpolated space. The difference actually can be told by this T homogeneous operators by this commuting condition. This measure is in this way, because any elements in LP, we did not define LP here, right? But we have to put it back to L1 to get its measure. Because for L1, we have that the integral d omega over d phi times d phi is equal to omega 1. Okay. Then if omega is a normal linear function, then this is finite. If it's a weight, then this usually will be infinity. So we have to require that this to be finite. Then we take all negative 1 over p homogeneous operates such that this piece power measure to be finite. Then there's an isometric isomorphism between the special LP space and the interpolated LP space. Is denoted by satisfying this equation with proper x. The Hargreaves LP space gives us the way to deal trace one. But usually we don't have trace, so we have to figure out a trace. Then we use cross product with respect to the left, the modular automorphism from tracer from left half weight. And let's say that is a dual action of R in N. Then with this trace, we can define the tau measure operates in N, but not in M. So we have to define the M's LP space. Then it is defined in this way. First, we take all tau measurable operates satisfy these special conditions. Theta S acting on X equal to E2 negative S over P. And this negative S over P gives us the elements in LP space. The measure is given by this one. Tau A, trace X equal to tau of chi. This chi is a spectral projection. Take a spectral projection of X to the power P from 1 to infinity. There's also an isometric isomorphism between Hargreaves LP space and Hillsum's LP space. The advantage of this Hargreaves LP space is that we can ignore the underlying Hilbert space because we can use tau measure operates and this special condition. Because the set of tau measurable operates is a complete Hausdorff topological space, and it's also an algebra with respect to strong product and strong sum. So somehow, we always use the information from the topology and the algebra. That means somehow we can ignore the underlying Hilbert space. But if we want, we can get it back, but sometimes it's a little complicated. There are also a wide fundamental inequality called Hölder's inequality. This X times Y is 2. R norm is less or equal to X's T norm times Y's S norm. This is expressed in terms of spatial LP space, but it also can be expressed in terms of Hargreaves LP space. And if this is similar, when this inequality becomes equality, it has this condition. This is similar to the commutative case. Now I'd like to introduce the Fourier transform. It's very important for Fourier transform in the classical group theory, especially in the theory of real lines. The Fourier transform of quantum group is introduced by Van Dell in 2007, but it is in algebraic case. Okay. Now, later it was also studied by Cooney and Kaspers. The Fourier transform is defined in this way. It's from LT to LT prime on the dual, and T prime and T and T prime are conjugates. It pulls this cosine omega to lambda omega. So it actually is a generalization of this Fourier. Okay, we have here this Fourier representation from L1 to L2. L2 here actually is trivial, right? Because we already identified them. But when we take the interpolation, this becomes non-trivial. Formally, we can write it in this way. Because we prefer the spatial, the expression of spatial LP space. Integral W is the multiplicative unitary x d phi to the power 1 over d prime times 1 over d. This x is in L1 intersection with L2, but it's not in special case. It's not in special LP. This should be in interpolate LP space. So in this case, we have to pull this interpolate LP space to the spatial LP space. But if you don't like to do that, you have to understand it as a limit case, right? Because if we take a proper x, we can always to let it make sense. It also have this this equation, integral ft x Fourier transform times y star d phi equal to integral x times the Fourier transform of the dual Fourier transform of y star. The hat of ft is the Fourier transform from the dual side to itself. This is a very important result for Fourier transform. It's called Hausdorff-Yang inequality. It was proved by Cooney in 2010. It was also proved by Kaspers in 2012. It tells us this x Fourier transform's t prime norm is less or equal to x's t norm. So we want to study the Hausdorff-Yang inequality further. We want to study its extremizer. we already proved we already obtained the extremizer for some inequality. We found that there are this special notation by shifts of group-like projection. This is first given by Jinsong Wu in 2017, and then it is improved by Jinsong Wu in 2018. It starts from a group-like projection. Group-like projection is similar to subgroup in group case. Also, there are similar notation by projection. It's a little different from group-like projection because it's defined from the Fourier transform. Okay. For unimodular case algebra, they are the same. No, they are not the same because it does not tell us whether it is finite. If it's finite, if a group-like projection is finite, then they are the same. Usually they are not. This is in okay. The biprojection for locally compatible group is inspired from subfactor theory because for subfactor theory, it already introduced these biprojections. Then by considering the translation, somehow it's the translation of this biprojection or group-like projection, we introduce a left shift group-like projection. If we take the Fourier transform of the module translation of the dual size, then we will get the bi-shift of group-like projection. So usually we say that this bi-shift of group-like projection is similar to the modulation and the translation of an open compact subgroup, because we take shift from itself and take the Fourier transform of shift from the dual at the same time to get this notation. Then we can prove the following result by using this bi-shift of group-like projection. Suppose G is a locally compatible, then the following are equivalent. If the Hausdorff inequality is an equality for some t less or equal to 2 greater than 1, then this indicates that this X has to be a bi-shift of a group-like projection. This is also equivalent to this one, the second one. But the second one is somehow easily from the first one. Okay. For group case, it's proved in 1974 and 1977 in 2 different ways. If we denote this CT to be the super of the portion of the 2 norms, then by using our result, we say, not our result, by Hausdorff inequality, this is less or equal to 1. The CT usually is not equal to 1. Usually is not equal to 1. This is the question we will ask it. We will ask later. We will ask later. Very important for Fourier analysis. Very important notation for Fourier analysis is convolution. For locally compatible groups, there are 3 ways to define convolutions. Actually, there are 3 different convolutions. The first one is using two normal linear functions. The second one is use normal linear functions and elements in the Fourier algebra. The third one is similar to the first one by changing the positions. If we graph it in this picture, it actually corresponds to this point. this point and this point. So it forms this triangle. It forms this triangle. In our study, we will split it into 4 ranges. The first two, the range 1 and range 2, is already proved in 2017 and 2018. That means RTS are less or equal to 2, greater or equal to 1. Then in this case, we can use the Cauchy net to define this convolution X star with rho negative I or T prime Y. This should be in LR phi. And the Fourier transform acting on this convolution, we will get the multiplication of the 2 Fourier transform. For the second range, that means R is greater or equal to 2 in the middle of this triangle. Then this definition is somehow simple. We can just use the Fourier transform. But not just one Fourier transform. Actually, we use 2, right? One is from itself to the dual. The other one is from dual to itself. Then we have the rest 2, 3, and 4. To define the rest 2 convolution, we have to introduce the pullback of involution. That means we have to pull the involution on the dual back to itself. There are 2 cases when t less or equal to 1, or less or equal to 2, greater or equal to 1. It's defined in this way. When this is t. When t less or equal to infinity, greater or equal to 2, we define in this way. That means we have to use use the Fourier transform, the dual Fourier transform. Note that this actually is dense in the LP space. If we take some special case, like t equal to infinity, this actually is the any point. So somehow we take the interpolation of any points and we did not introduce the t equal to 1. Actually, they already know. They can find in Kussmann and Vasquez's paper. They also use, I think they also use this notation. Actually, it's the interpolation between this hash and for t equal to 1 and any point. They have some property and bad property. Like this operation does not commute with the involution. It also does not. It neither does not satisfy this inequality, but it acts well on this convolution. This is okay. I misplaced this equation here. We should put later. X hash to the x to hash is x. It also commute with this involution in this way. Then we can define the convolution for 4 ranges. And if we put this special case d omega over d phi, we will get this omega times L, tensor L times delta A back. We also will get this back. And we also can give the Yang inequalities. For range 1, this is proved in 2017. This is proved in 2018. For the rest two, it's proved recently. But for Katz algebra, we can put the four ranges. We can put the formulations for four ranges together in one single formula in this way, because Katz algebra has some nice properties. We also can characterize its extremizer, similar to the Hausdorff-Yancey inequalities case. There are bishifts of group-like projection satisfying certain conditions, because there are two, so there are some, for four different cases, there are four different conditions. I'm not going to list it here. For unimodular Katz algebra, we also have this inequality. X star y to the R norm is less than or equal to absolute value of X star absolute value of y, so norm to the power 1/2 times X star's absolute value times Y star's absolute values to the power R. This R norm to the power 1/2. But I cannot prove it for locally compact quantum group. I think it should be true for a suitable form. Also, we can conclude some results for Yancey inequality by considering this super. So because we are short of time, I'm going to briefly introduce some results. We also can prove this entropy convolution inequality by differential Yancey inequality. For R's case, this actually is entropy power inequality. But for general case, we cannot obtain this entropy power inequality. Maybe for some special case, we can obtain entropy power inequality. Also, we can use Hausdorff-Yancey inequality to obtain Donato-Stark uncertainty principle. And we can also characterize its extremizer. There are bishift of biprojections. There are bishift of biprojections. And we also can prove Birchman-Buckner uncertainty principle. And the extremizer is also bishift of group-like projections. Similar to the real case, we have this hardest uncertainty principle. But this is a little weaker than the real case. We actually obtain a stronger case for locally, not for locally compact quantum group. It's for unitary modular Katz algebra. So for the trace case, we have better results, but for the general case, we don't have that. Our proof for the extremizer of Yancey inequality for locally compact quantum is different from the subfact case. For subfact case, we use the sunset estimate, and we also prove that this sunset estimate is good for unimodular Katz algebra. Unfortunately, it's not good for locally compact quantum group, at least in this form. Okay, we also expect the right form for locally compact quantum group because it's very useful for some analysis. We also obtain this Minkowski inequality. For locally compact group, this somehow is useful. And we can obtain this for locally compact quantum. but I still not find its application, but I believe it should be useful. Okay. We also study some positivity, like a sure product theory. Sure product theory is very powerful in our recent paper to determine whether a fusion ring is a quadratic ring for a fusion category. But for locally compatible group, we don't have the right formulation for sure product theory. We only have this formulation for Kessel algebra, but I think it's still not good enough. It's not good to use. It has nice form for unimodular Kessel algebra, okay, because we can drop this delta and we can drop this number 5. So maybe we should find a better formulation for locally compatible because it's somehow is useful for finite case. It should be somehow useful for infinite case, I guess. The positive definity is we generalize the positive definity to LP case. Okay. For t less or equal to 2, we can just require its Fourier transform to be greater or equal to 0. But for t less or equal to infinity greater than 2, we use the convolution to define its positivity. This already studied well by Dawes Selmy in 2017, and this 13, and Rudy Weissert in 2014. But they did not study for the LP case. They studied for t equal to infinity. I guess the result is also good for LP, but I cannot prove it right now. There are also an important notation for locally compatible. It's called amenability. There are many mathematicians studying it, but there are also an open question for it, whether the commutability of the dual implies the amenability of the locally compatible, whether the amenability of locally compatible group imply the commutability of the dual. Also, the idempotent states, which is, in my point, it's generalized somehow. It's generalized the group-like projection somehow. It well studied by Selmy, Paul, France, Scar, etc. We are very interested in sharp Hausdorff-Yang inequality, but as we know, they only studied for Lie groups, like Klein, Russell in 1978, Colin, Martin, Mueller passed it recently, and also Seiden sets by 1. This is Simon Wan, a student of Professor Xu, Wanhua. And there are also many interesting topics related to Fourier transform. So we have the following questions. Can we find the norm of Fourier transform for locally compatible group? That means we have to remove the condition, the restriction between t and t prime. The second question: how can we find the best constant Ct for proper proper locally compact quantum group? The third question I think might be simple. Whether is it true that Ct equal to the dual Ct? where the dual city is the best constant for the dual. And we can ask a similar question for the best constant CT for Yang inequality. And I think there's the relation between Yang inequality and best. I think this is true. The relation between best constant for Yang inequality and the best constant for Hausdorff-Yang inequality. The number 7 is to find the reverse Yang inequality. For commutative case, it's not very hard, but for non-commutative, even for finite case, it seems that this at least is not unique. I don't know which one is better. Also, we can try to figure out what is the right expression for fractional Yang inequality and prove them. This is not easy. This is not easy. Even for finite case, for group case, it's not known. So there's some bigger problem. What is the right formulation for the Braskamp-Lieb inequality? Because the Braskamp-Lieb inequality generalizes Yang inequality. Also, maybe as I said before, we can try to find the right formulation for some set estimation. And I don't know whether the minimizer of the entropy convolution inequality. I guess it should be left shift of group-like position. We can prove it for unimodular case algebra, but we cannot prove it for locally compact quantum. And there's also a question for positive definite. There are also a project for Fourier multiple or locally compact quantum group by small one. Also, what is the perturbation theory for like uncertainty principle and related theory? We don't know yet, but we think there should be one, but it's not easy. Also, I think this is also a fundamental question for our quantum Fourier analysis. What is the relation between Fourier transform and the differentiation? Somehow, in some case, it should be quantum differentiation. That is my talk. Thank you.
Thank you, Jinsong, for an absolutely beautiful talk and for so many interesting questions. It's nice to see you solved many problems, but you opened up many new ones. So I'm sure there are many questions. People can unmute themselves and ask questions.
May I ask a question?
Of course.
I think a locally compact quantum group is infinite dimensional.
Could you identify
Yes.
yourself? Say who you are.
This is Min Cho from New York University.
Yeah.
Okay. So a locally compact quantum group is infinite dimensional, but then how do you define a measure on G? How do you define the LP space? Like how do you construct a measure? It's infinite dimensional.
This measure is already defined in this definition. We require it here. This is the measure. The hard weight is the measure. We take this as measure.
Oh, I see.
Yeah, that is why I have to say the work by Voronovich. It is very important because he can construct from compact quantum group.
So
Hard weight.
Because the left and right hard weights are different, does that mean that the measure is not actually translation invariant?
if we write it in this way, it's what do you mean by translate invariant?
Like I'm thinking of something
Because,
similar to looping measure.
because the mutability actually tells us the invariant and the translation. Our translation here is actually is convolution. So when we say invariant, actually is this equation.
Oh, I see.
So there's some similar notation. You should you should say whether you exactly mean. This is I think your meaning is this equation. Yeah, this is invariant and this one.
Oh, I see. Thank you.
Okay.
I should mention that we're very pleased and honored today to have Voronovich as a listener. Perhaps you have some comment.
Yeah, I have a question. So what kind of a topology you can endow these groups?
But wait, but Red, maybe.
Yeah.
Okay. What topology? I did not hear your questions, sorry.
Oh, yeah. So what kind of a topology you can associate with these locally compact quantum groups?
What kind of topology we can associate to this locally compact quantum? If we associate this for non-algebra, there are a lot of topologies. We can use the normal topology, weakly operator topology, and strong operator topology, etc. But for LP space, then usually we can associate two topology. The topology from the norm, and the other one is the weak one.
Yeah. Yeah.
So there are a lot of topology we can use.
So Voronovich, do you have some comment?
I'm sorry, I'm too old to comment such a beautiful work. So I am very impressed simply.
Thank you.
Thank you.
At some moment, I was thinking about finding the best entropy constant. I mean, when you take entropy of, when you take a state, say, a vector in the Hilbert space, then it defines measure on G and G hat, and you may define entropy of the two measures, sum them, and then the sum. Oh yeah, it's on the screen now, and it's a question: what is? Can you improve the zero here? This formula here.
This zero actually means.
For example, if you take as a group, you take the group of real numbers. I mean, the group R. That it is known that this is, you can write here some
this actually is zero. This is, if we take a group R, this actually becomes the usual entropy, because this term elements, there's no here, no this one. It becomes zero. So it is exactly the usual one. Actually, this is the same as this is the same the relative entropy. Also is the same as the usual one. If we take R, this is D5. There's no special derivative. This is become zero. For this one,
yeah.
Maybe I can also use this one here because they are the same. They are the same. This one is the same as that one. The difference is that this one we use a vector. Here we use a state. Okay, we use a state. Then this integral here will become a trace. And this will be, for R, this will be 0. Okay, this will be 0. So it's simply the special derivative times the log special derivative. Okay, then take the trace and negative of this term minus this term.
For the entropy,
So
Okay, I'm not ready for the discussion, so forgive me my remark.
what I'd like to say, this actually is not a new notation. It's not a, it's not a new notation. We just use a new formulation here.
is the lower bound on the entropy inequality known to be 0?
Pardon?
Is the lower bound on the entropy inequality known to be 0?
You mean this one? This lower bound of the lower bound of this one is 0, right? But the lower bound of this entropy is not 0.
No, but you claim that the sum is strictly positive.
Yeah, the sum
Right.
is strictly positive, but for the single term,
Okay.
for this
Can
term,
you
it's
replace 0 here by some other number which is positive? So you will get you will
Yeah, that is the
can you have some stronger inequality
this is the
where
good
0
question.
is replaced by
What's
some positive number.
Yes. This
And
is a
this
good question.
number probably depends on the group and say on the deformation
Yes,
parameter and things
it
like
depends
that.
on group.
It's a question
Yeah.
how to compute this number and whether does it depends on the deformation parameters and when you take E2 group.
Yeah, you're right. This is what I'm working on. I'm trying to find. I'm trying to replace this 0 to a strictly positive one. But I currently I computed your examples, and unfortunately I think the lower bound is not strictly positive. Sorry.
I think about 20 years ago, we tried with Fons van Daal to solve this problem, but with no result.
Okay. So maybe I should find a better example.
Okay.
So are there other questions? Any other questions? Well, if there are no other questions, then we thank you again, Jinsong. It was absolutely beautiful talk, and we look forward not only to this paper, but to all the future papers on this subject. Maybe people can unmute themselves and applaud for you.
Thank you.
So we'll see next week, talk by Nilanjana Datta. Bye-bye. Bye-bye.